Section 12.1, One-Way ANOVA, Key Concept. In this section, we introduce the method of one-way analysis of variance, which is used for tests of hypotheses that three or more populations have means that are all equal, as in the null hypothesis being population mean 1 is equal to population mean 2, which is equal to population mean 3. Because the calculations are very complicated, we emphasize the interpretation of results obtained by using technology. Now, we have what we call as the F distribution. The F distribution, there is a different F distribution for each different pair of degrees of freedom for numerator and denominator. The F distribution is not symmetric, it is skewed right, as you can see the picture over here to the right. The values of the F distribution cannot be negative, and the exact shape of the F distribution depends on the two different degrees of freedom. So here we have alpha, which is going to be in the right, and again it's not symmetric because it's skewed right, and again our values are non-negative. One-way analysis of variance, another way we call this is ANOVA. When testing for equality of three or more population means, use the method of one-way analysis of variance. One-way analysis of variance, also called ANOVA, is a method of testing the equality of three or more population means by analyzing sample variances. One-way analysis of variance is used with data categorized with one factor or treatment. So there is one characteristic used to separate the sample data into different categories. The term treatment is used because early applications of analysis of variance involved agricultural experiments in which different plots of farmland were treated with different fertilizers, seed types, insecticides, and so on. Now, Table 12.1 uses the one treatment or factor of size category of the automobile. The factor of size has four different categories: small, mid-size, large, and SUV, and we'll be using that for the first example. Now, here is the breakdown of the one-way analysis of variance for testing equality of three or more population means. The objective: use samples from three or more different populations to test a claim that the populations all have the same mean. Requirements: 1. The populations have distributions that are approximately normal. 2. The populations have the same variance or standard deviation. 3. The samples are simple random samples of quantitative data. 4. The samples are independent of each other. 5. The different samples are from populations that are categorized in only one way. Step 1, you want to identify the null and the alternative hypothesis. So how do you structure an analysis of variance hypothesis test? So the null is always going to have the equality like before. But in this case here, depending on how many samples that you're comparing, you have mean 1, population mean 2 equals population mean 3, depending on how many samples you have. Now, the alternative is always going to be this: at least one of the means is different from the others. Step 2, you select the significance level alpha. And again, based on the seriousness of a type 1 error, you make alpha small if the consequences of rejecting a true null hypothesis are severe, and the values of 0.05 and 0.01 are very common. Okay, so we have step 3, which is the p-value method, so let's go ahead and discuss that first. So you're going to use technology to obtain results that include the test statistic and the p-value. Using StatCrunch, you're going to click Stat on the top of the menu. You're going to select ANOVA from the drop-down menu, then select One Way from the submenu. Number 3, you select the columns to be included in the analysis, and then you click Compute. Now, when you're using the critical value method, you're finding the critical value. The critical value of F is found by using Table A5 and assuming a right-tailed test because large values of F correspond to significant differences among means, with K samples each having n values. The numbers of degrees of freedom are as follows. degrees of freedom using k, which is equal to the number of samples, and n is equal to the sample size. So the numerator degrees of freedom is equal to k minus 1, which is the number of samples minus 1. And the denominator degrees of freedom is the number of samples times the quantity, the sample size minus 1. Now in step 4, you want to identify the test statistic and the p-value from the display. Now again, the ANOVA test is a right tail test because only large values of the test statistic cause us to reject equality of the population means. So we reject the null if the p-value is less than or equal to the significance level. So reject the null hypothesis of equal means and conclude that at least one of the population means is different from the others. You fail to reject the null if the p-value is greater than the significance level, and you fail to reject the null hypothesis of equal means. For the critical value method, we reject the null if the test statistic is in the critical region, and we fail to reject the null if the test statistic is not in the critical region. And then we're going to state the conclusion. Now, for the original claim, it's going to include equality because that's what we're testing, is the equality. And if we reject the null, then we would say that there is sufficient evidence to warrant rejection the claim that of the original claim. And then if the original claim includes equality and we fail to reject the null hypothesis, then we would say that there is not sufficient evidence to warrant rejection the claim that followed by the original claim. Now, because the calculations required for one-way analysis of variances are messy, we recommend using technology with this study strategy. Number one, you want to understand that a small p-value, such as 0.05 or less, leads to rejection of the null hypothesis of equal means. That means if the p-value, or if p is low, then the null must go. Now, with a large p-value, such as greater than 0.05, you fail to reject the null hypothesis of equal means. Then number two, you develop an understanding of the underlying rationale by studying the examples in this section.